Okay.
Perfect. Yeah. And would you also please upload your slides afterwards?
Yeah, sure. I didn't. No, sorry.
That's okay.
Okay.
So you have, I guess it isn't. It's a poster time slot, if I'm not mistaken.
Yep.
So you have let's say around 10 minutes to summarize the poster. Please go ahead.
Yep. Okay. So I would talk about a new muon tracking algorithm for the level 1 trigger in the CMS barrel muon chambers during high luminosity LHC. So first, I will talk a brief introduction about the CMS experiment and also high lumi. So first, this is a diagram of one of the wheels, the 5 wheels of CMS. Here you can see all the subdetectors that are in the barrel from the inner tracker to the muon chambers. So talking about the muon chambers, we can see here that, well, in the barrel, we have both the resistive plate chambers or RPCs and also the drift tube chambers or DTs. So each of these wheels is divided in 12 sectors, and each sector is divided also in 4 chambers. So we've got 4 DT chambers on each sector. So each chamber is divided in 3 super layers, one in theta view and the other 2 in the free view. And each super layer is made of 4 layers that are displaced half a cell between them. Also, each layer has around 50 to 100 cells. So a basic functioning of these drift tube cells, when a charged particle passes through the cell, and ionize the gas that is inside. So the particles that are ionized drift toward the wire with constant drift velocity. So we can measure with associated electronics the time of the avalanche upon reaching the wire, and we can extract precise coordinates by pattern reconstruction. Something that you need to know is that we've got a left-right, or what we call laterality ambiguity, on the hit position. So a bit about high lumi LHC. This will be an LHC upgrade that will occur during 2025-27 shutdown. So it will imply an increase in the LHC instantaneous luminosity from the present 2 times 10 to the 34 to around 7.5. So this increasing makes necessary to upgrade certain subdetectors, because the expected radiation doses and the background and CMS readout rate will increase quite a lot because these updates. So for the DT chambers, it will imply that the present on detector electronics that limit the trigger rate from, well, around 100 kilohertz, we need to substitute them to reach the 750 kilohertz that we need. So we are going to use a new phase 2 system that will digitalize all the detector signals and will send them to a new electronic backend system that will be in the service cavern, and we will be in charge of generating these trigger primitives and also do the event matching. So let's talk about the analytical method. This is an algorithm that generates these trigger primitives for high luminosity LHC. So this algorithm profits from the better electronics time binning that we will have in phase 2, that is 1 nanosecond instead of the present 12.5 nanoseconds. So the algorithm is capable of computing the trigger primitives crossing time, both in nanoseconds and also in bunch crossing units, and also other track parameters like the position and the local direction. And we expect to reach a resolution close to the present offline resolution. So the algorithm is implemented both in software as an emulator and also in firmware. And the inputs of this algorithm are the time and the cell number of all the signals that are detected in a single superlayer, well, the 2 superlayers in a different way. And also it assumes that the muons follow straight paths inside the chambers. So it's developed the algorithm in 3 steps. The first one is the grouping. So the algorithm selects patterns of 3 or 4 DT fire cells that are compatible with straight lines only in a single superlayer, and also their subpatterns of 3 cells. Then the fitting, so for these groups that the grouping identify, it computes unambiguously the bunch crossing using the mean timer property, and also the other track parameters using exact formulas that are obtained using chi-square minimization. And at the end, the correlation attempts to combine the compatible tracks that we obtained from the single superlayers and then recomputes the superlayer track parameters so it can profit from the larger level arm that we have between superlayers. Also, we apply several cleaning filters at several states that I'm not going to explain because I don't have that time. And after that, after building the analytical method DD primitives and clustering the RPC hits, we can combine the information from both the subdetectors in what we call a super primitive So this way we can exploit the redundancy and complementarity of the two subsystems, and then combine the good DT spatial resolution and the good RPC time resolution. So now we are going to test how the algorithm performs. So first, we would like to evaluate it in simulation. So we use a sample of simulated single muons with an average pileup of 200 collisions per yes. So we compute efficiencies. We compute them with respect to offline segments, so segments reconstructed with the offline system, and we apply them several quality cuts, and also we match them geometrically to the generated muons of the sample. And also we will consider efficient only the trigger primitives that are in the right BX. So also for sector phi and bending phi resolutions that are the same, almost the same, that position and direction, but in global coordinates. So we compute them with respect to the simulated hits that we have in the muon chambers. And well, apart from this, in the following plots, I will show results that use and doesn't use the RPC system. And also I will consider the DT aging scenario that is predicted, well, the DT and RPC, sorry, aging scenario that is predicted at the end of HL-LHC that you can see in the backup. So here, as I said, I'm showing the trigger primitive efficiency with respect to reconstructed segments. So for instance, in the MV1 standard wheels, we see that when we apply the aging, the end of HL-LHC aging, the DT only efficiency decreases quite a lot, around 30, well, it reaches 70%, because this is the chambers, if you go to the backup, that are more expected to suffer from the aging. But when on top of this, we add the RPCs, the efficiency recovers up to 92%, let's say. But in general, the efficiency reaches 98% at most, well, which is on the bottom level. And then resolutions on the bottom right, you can see the trigger time distribution. So you can see that the core resolutions of all the distributions is less than 2.5 nanoseconds. Also reaching, when adding RPCs, it reaches 1.9 nanoseconds. And on the left, you can see on the top the sector 5 resolution, and on the bottom the bending phi. So for sector 5, as an example, you can see that the MV2 stations show a sector phi resolutions of around 0.03 milliradians, and this reflects an improvement of around 6 times the resolutions that we have in the phase 1 system, in the legacy system. And on the bending phi resolution, we can see a similar improvement. That is, well, the resolution is around 1 milliradian, so yeah, it's a very huge improvement. So about the firmware status, as I said, the analytical method is already implemented in firmware, concretely in a Xilinx Virtual 7 FPGA, and it's written in VHDL. So the present implementation includes the analytical method algorithm without using the RPCs, plus also the readout, slow control, TCDS, etc. So we've got a test stand at CMS in Madrid that allows to perform dedicated tests of this firmware. So what we do is we inject the hits from all the chambers of the CMS detector, and then we generate and read the trigger primitives, and we compare them to the ones that we take with the same hits by the software emulator. So here in both plots, sorry, we are injecting hits from selected set to mu events that were taken in 2016. So they are from real collision data. So when we compare the primitives that are obtained both in firmware and emulator with the same hits and lateralities, we reach an agreement in fitted time, position, and local direction of the least significant bit. And also, apart from this, we have performed what we call the DT slice test. So it consists of one CMS sector that is being instrumented with the new front-end and back-end prototype, sorry. So this way we can test in the real CMS, in the real conditions in CMS infrastructure, both phase 1 and phase 2 electronics at the same time. So one of these backend boards that we call the AB7 runs the analytical method firmware. So we can validate both the firmware and the algorithm itself using real cosmic muons. So here in this plot, I show the difference between both, well, the trigger primitives fitted time and the offline reconstructed segment time using the phase 2 trigger primitives, so the new primitives, using a cosmic muon sample that was collected in the slice test setup in that specific chamber. So the core sigma of the distribution is around 3 nanoseconds. So we need to say that while for the phase 1 system, we've got a trigger output time that is in BX units, so it has a 25 nanosecond step. For phase 2, we've got an inherent online time that, as you can see, it's around a few nanoseconds. So it's a huge improvement that, well, it will do a lot. So just to conclude, In this talk, we have proposed a new algorithm for the phase 2 DT electronic system. It obtains quite good efficiencies and resolutions. Also, the algorithm is already implemented in firmware and is being tested in a test bench with injected hits from real collision data, and also is being tested in the real CMS with real cosmics, so directly on the detector. And further steps that we want to take, we would like to include the theta superlayer because we are not using it at all right now. So we will like to include it in the algorithm, and also the RPC hits in the firmware implementation. And also we would like to integrate the system with the next trigger levels. So, well, you can see more details about this talk in the level 1 trigger phase 2 upgrade TDR that has been released a couple of months ago. And I think that's all. Thank you very much.
Thank you very much for this nice and brief overview. Do we have maybe 1 or 2 quick questions? If not, then maybe we get more questions during the discussion sessions.
Sure.
I'll propose to move on as we are running a tiny bit late, not too bad. So thanks again.
Thank you very much.
And please upload your slides as well, because
yeah, sure. Right
perfect.
Now. Thank you.
Excellent. Then we will move to Jenny.
Yes, hello, can you hear me?
Yes, we can hear and see you perfectly.
Perfect. Let's see if share the screen also.
So, yes, now we